Hi, and welcome to the first real episode in this series where I try and turn this keyboard into a portable synthesizer. So, in the last episode we just spent a lot of time talking, but in this episode we're actually going to get started. So, if you want to get started on an embedded project, it can be pretty daunting to try and choose the right hardware. There's a lot of different options and external components, and so it's pretty difficult to know exactly what you actually need and how to choose that. So the way I do it is I start with the requirements for my project. So the first requirement is to be able to play audio. So in order to do that, we're going to need some kind of digital to analog converter, which is called a DAC. And this could either be internal inside the microcontroller, or it could be an external board such as this one. If it is an external board, we're going to need to use I2S, which is a communications protocol, which will allow us to send audio data to this DAC, and then this will handle that and play the audio. In order to play audio, you need to have a high clock frequency on your CPU, which means that you need to calculate a lot of things. In my previous project, my microcontroller had a 100 megahertz CPU, and that got me around 6 voice polyphony and some basic effects on the subtractive synthesizer. In this project, I want to do a lot more, so I was thinking we probably need around 300 megahertz. Okay, so the next requirement is we are going to be talking to this keyboard, and so we need to somehow interface with the keyboard. And usually when you're talking about keyboards, there's two protocols you'll be talking about, which is either the PS2 protocol, which is what this one is. It's got this old school connector, or you can use USB. Okay, next requirement, we need to interface with a screen so that the user can see certain things. We have a user interface and it can display information, right? So most of these kind of screens that you can buy off the internet will have their own dedicated microcontroller inside them, and we just sort of send signals through this protocol called SPI. So when we're talking about these requirements, they basically split into two categories. We've got the interface and we've got the audio processing part, right? So the interface is sort of like the keyboard and the screen, which is what the user sees, and then the audio processing is kind of like the back end, which is what's going on behind the scenes and is eventually outputted to the DAC. And when you're thinking about these two things, they're basically quite different. So the interface side of things is unpredictable, right? Because it relies on user inputs. So if the user's not pressing anything, it doesn't really have to process much. But if all of a sudden the user starts pressing loads of buttons, then suddenly it's going to have to do a lot more processing. All in all, though, the interface side of things doesn't actually require many calculations or much processing power. And lastly, all of this stuff is a bit timing insensitive. And what I mean by that is that if I press a button and then 5 milliseconds later the thing reacts, I'm probably not going to notice, right? So there's a bit of leeway. In contrast, we have the audio processing. And now this is actually extremely predictable because we always have to produce the same number of samples every second. We always have to produce 32,000 samples every single second. And that number never changes. So the amount of work that the CPU has to do remains constant. It also has pretty high processing requirements. If you've ever done digital signal processing, you have to do a lot of calculations, 32,000 calculations a second, and then you have to do filters, effects, that just adds more and more calculations. And so you actually need a pretty powerful CPU. And it is extremely timing sensitive, which is, in contrast to the interface side of things, if there's a delay of 5 milliseconds, that can ruin everything because you need to have your samples ready the moment that the DAC wants them. And if you don't have them ready, what you're going to hear are a lot of glitches, and it's going to make a lot of weird clicking sounds. So you really need to make sure you have all these samples calculated in time. So it's extremely timing sensitive. And so because these two things are quite different, I think it's best to use two different microcontrollers for these two separate tasks. So you're going to have one microcontroller controlling the front end, and then you're going to have one doing the audio generation, which is timing sensitive. So that one can just be dedicated to its single task without being interrupted by the user, without being interrupted by needing to update the screen, and so on. So if we put all of that stuff together, what requirements do we end up with? So for the protocols, we need SPI, which is for the screen. We need I2S, which is for the DAC, digital audio converter. We need USART for the communication between the two microcontrollers. We need USB or PS2 for the keyboard, and we need sufficient pins for all of this combined. Okay, now for the specs, we probably need around 300 megahertz for the audio processing with floating point unit. We need about this much memory, and we need about this much storage, and it would be ideal actually if we could get an SD card, so then you could load things from the computer. So with all of that in mind, here's the sort of general architecture that we're going to be using. So we have the keyboard here, which is going to be communicating via USB to the front end microcontroller. The microcontroller also gets various inputs that we might add later, like MIDI, audio in, expression pedal. I don't exactly have concrete plans for that right now, but you know, in the future we might want to add these kind of things. And then it'll also use SPI to communicate with the screen, and then we'll use USART to communicate with the audio microcontroller, which is of our back end. That in turn will use I2S to communicate with the DAC, and then the DAC will generate our audio signal. Okay, so with all of that in mind, what hardware have I chosen? The microcontroller we're going to be using here is the TNC 4.1. I've chosen that because it basically fits all the requirements, and if it fits all the requirements, then it should be good to go, right? So it's got all the protocols I mentioned. It's got USB. It's got a really powerful processor, 600 megahertz. It's got 1 megabyte memory, which is quite a lot for a microcontroller, believe it or not. And we can even expand that up to 8 megabytes, which is pretty nice. I'm going to use basically 2 of these, so both of the microcontrollers are going to be TNC. And the reason I'm using both is because they're pretty cheap, and as you can see, they're pretty powerful. So I think that I'm never going to run into many problems when I'm using this in terms of not having enough processing power, right? For my DAC, I'm using this, the UDA 1334A, which is what I used in my previous project on the organ. Nothing much to say about this really. It's got a DAC, it's got a headphone port, which is pretty useful. It's cheap, it's reliable, and it's proven to work. For the keyboard, you saw this in the last episode, we're using this guy, the IBM keyboard. Alright, it turns out we have a bit of a problem. So I've got the keyboard here connected to my computer just to test it out. Indeed, it does seem to work, but see, if we press keys, everything seems fine. But if we try and press, let's say, 4 keys at the same time, only 2 of them actually register. And this is kind of a deal breaker, because if we want to play chords in a song, you know, being able to play many things at once is quite important, and on this keyboard we can't actually do that. So I actually think that this keyboard might not be the one, and we might have to find a different keyboard. So instead we've got this gaming keyboard as our replacement. So this is a modern keyboard, and because it's a gaming keyboard, it has this thing called N key rollover, which basically just means I can hold down any number of keys and it will process all of them, which is really nice and exactly what I wanted. It does use USB, which I did think originally was going to be a lot more complicated than PS2. Now the protocol of USB is a lot more complicated. However, luckily for me, the TNC board actually implements USB on hardware level, and there's also a handy library that's been written for me, so I don't actually have to do any work to get this working in theory. When we look at the wires inside of a USB cable, we're going to see 4 wires. So you've got your standard power and ground, and then you have 2 data lines, the D- and D+. So I said this was implemented in the hardware, and we can see on the TNC board here, we have these 4 pins, actually 5 pins, which are going to be used for our USB host. So the microcontroller is going to be the host, and the keyboard is going to be the device. It actually has 2 grounds. This is seemingly for historical reasons, which I'm not entirely clear on. But we're going to ignore the second ground, and so we're just going to use these 4. So we've got the 5 volts, the D-, the D+. And then once we have this plugged in, we can use this library, which is written by the creators of TNC, and hopefully everything should just work. So without any further ado, let's get started building. Alright, here we have the TNC board in real life. As you can see here, what I've done is I've just soldered on all of the pins, and I plugged it into a breadboard. And then over here, I have my USB connections, and I've soldered them like this. You need to make sure you leave pin 5 because that's the second ground that we're going to ignore, and just use the first 4 pins. So we also have this USB breakout board, and you can see that there's 4 connections here. You've got the V bus, which corresponds to the 5 volts, the D minus, D plus, and the ground. So, I mean, plugging this in is pretty simple. So we're just going to plug it separately on the side here. So once we have this guy in, we can then get this ribbon cable here and plug them in. So we've got this side plugged in, you can see there. Whoop. So the yellow's on the left here and the brown is on the right, so we need to make sure we maintain that orientation so that the ground will go to the ground and the 5 volt will go to the 5 volt. So you can check the website for the pinout on that and just verify everything's correct. Yep, you've got the brown on this side, the brown on that side. Yep, looks all good. So once we have that, we can get our keyboard here, and all we need to do is plug this guy in. And there we go. That's all we're going to do for this episode on the hardware side of things. Okay, let's get started on coding this thing. So what I have here is Visual Studio Code, and I've installed the Platform IO extension. So once you've got Platform IO installed, we can now create a new project, and we'll call this synth TNC. And we can select our board here. So that's going to be the TNC 4.1. And we can use the default location. So let's do that. So once we have this, we want to go into the menu on the right here and go to Libraries. And here we can search for the USB host library. And the one you want is the one USB host T36, which is written for the TNC board specifically. So we'll click on that. We'll add it to our project. So once we have that, we can head on over to the GitHub page here, because they have a bunch of examples, and the example we want to pull is this keyboard one here. So we're just going to open this, and I'm just going to copy the whole file. Now we're going to go into our main file, and we're just going to paste in the example. Okay, so down here we have the board, we've got the keyboard, and then we've got my computer here. Alright, so hopefully this should just work. So we're going to upload it here. So if I press a key on the keyboard, you can see that the microcontroller is receiving it. If you look closely, you can see that it's receiving the right keys. So that seems to work. Great. Okay, so that's pretty much it for this episode, but I just want to recommend a few things. First of all, there's this great video by Ben Eater called the USB Protocol, and he sort of dives much deeper than I did into how does the keyboard communicate with a computer, and how does this packet stuff work, and how do you actually get the data out of it. Like I said, I don't really want to go into detail because it's not really relevant. If it's all done for us, we don't really need to know. Lastly, there's going to be a few links in the description. There's going to be the source code for this project. I'm going to write a code blog, so I don't want to explain everything in video format when it comes to the code. I think that a written format is actually better because you can sort of reread things and scroll up and down and stuff. So I'll be doing a code blog to actually explain the code. In these episodes, you're just going to get a sort of high-level overview. And then there's a few further reading materials about the USB protocol. Next time, we're going to get into digital audio basics. So we're going to use our DAC, and we're going to make our very first sounds, which should be a bit exciting to actually make something that's actually a synthesizer instead of just messing around with a keyboard. All right, that's everything. So thanks for watching, and I hope to see you next time.